Okay, in this video, I will show you the graph of some other exponential functions. Now, so far, we have seen that the graph of the exponential function 2 to the x, it looks like this, right? So the graph goes up to the right. And we said the graph has the y-intercept 0, 1. So the graph passes this point 0, 1 on the y-axis. Now, let me show you what does the graph of this exponential function look like. Gx equals 1/3 to the power of x. So now I'm gonna graph this function. So I'm gonna choose some random values for x and then compute the corresponding y values. Let's say we choose x to be -2, -1, 0, 1, 2, 3. Now when x equals -2, y equals 1/3 to the power of -2, and 1/3 to the power of -2, this is equal to 1 over 1/3 to the power of +2. So that is a 1 over 1/3 times 1/3. So it's 1 over 9, which is equal to 9. So when x equals -2, y equals 9. And when x equals -1, y equals 1/3 to the power of -1. So that is a +3. And when x equals 0, y equals 1/3 to the power of 0. And that is 1. And when x equals 1, y equals 1/3. And when x equals 2, y equals 1/3 to the power of 2. So that is a 1 over 9. And when x equals 3, y is a 1/3 to the power of 3. So that is a 1 over 27. So now I have found these points: -2, 9, -1, 3, 0, 1, 1, 1/3, and 2, 1 over 9, 3, 1 over 27. Okay, now if you plot these points on the xy coordinate system, you 1 over 9, 3, 1 over 27. Now, by connecting these points, you will get the graph of the function gx equals 1 over 3 to the power of power of x. Now this time what we can notice is the graph. It still passes the point 0, 1. Okay, so it has the same y-intercept as the function fx equals 2 to the x. But the difference is now the graph it goes down to the right, and this kind of graph we call it the decreasing function, because here the property is as the x values is getting bigger. You see, as the x value is getting bigger, -1, 0, +1, 2, 3, 4, the y values are getting smaller. So 3, 2, 1. See, as x values are getting bigger, the y values are getting smaller, from 9 to 3, from 3 to 1, from 1 to 1/3 to 1/9 to 1/27. So this function is called a decreasing function. And another thing in common is both functions they don't have any x-intercept, because the graph, if you look at the graph very close, the graph it will never touch the x-axis. It will never touch the x-axis. It can be very close, but it will never touch. And this is true for both functions. So so we can generalize the properties of the exponential function into this way. Say we have a exponential function e to the x, where b is greater than 0 and b is not equal to 1. If b is greater than 1, then the graph of the function goes up to the right, and the function is an increasing function. And if b is less than 1, then the graph of the function goes down to the right. And this time the function is a decreasing function. Now, both functions have the y-intercept 0, 1. And there is no x-intercept. There's no x-intercept. And if we consider the domain, because as the definition of the exponential function says, the domain can be any real number. X can be any real number. So the domain is from negative infinity to positive infinity. So here are the properties of the graphs of exponential functions. Okay. Let's take a look at some other examples. Let's see, I want to graph the function 4 to the x. Now, because the base is 4, it's greater than 1. So before I graph the function, we can anticipate the function is an increasing function, right? See, the function is an increasing function. The graph goes up to the right. And if I want to graph, for example, 3/2 to the x, can you guess what does the function look like? Yeah, the function still be an increasing function because 3/2 is still greater than 1, right? But if I graph function 2/3 to the x, this time the function will be a decreasing function because right now the base is less than 1. And you will see if we try to have the base to be a negative number, then we're not able to define the function because we said for the exponential function, the base has to be positive,